Let's get going. Welcome to Monday. Hope you guys had a good weekend. First things first, Yotem, who is a classmate in this class or the other class? In this class, asked me if he could speak for 1 minute on the Tufts Data Science group, which I don't know anything about yet, but it actually sounds kind of cool. So over to you.
So what's up, guys? As Chris said, my name is Yotam. I'm here to announce the GIM for the Tufts Data Science Club. It's tonight at 9 p.m. It's a new group club starting this year. We're going to focus about how you can apply data science to industry, to academia. We already have a bunch of speakers lined up this year, and it's a really exciting field. So I hope you guys can all show up. So yeah, thank you.
GIM is General Informational Meeting. Is that what? Interest. General Interest Meeting.
There's
I don't
also
know
going to be some information, but it's the interest is
Okay.
point.
All right. Anybody have any questions? All right. Thanks, Yotem. Okay. Let's see if this will come up here. Maybe. Oh, hang on. There we go. All right. Okay, so here's what we're going to talk about today. We are going to start talking about this recursion idea. Now, last week, a number of people said that you'd already seen recursion a little bit in Comp 11, and then I saw some I didn't get it, or it was crazy, or whatever, which is fine. We are going to go over it in detail today. It's really not as hard as you might think. All recursion is a function calling itself, and there's some bookkeeping to making sure that it actually works out all right. Okay? Hey guys. Shh. Thank you. All right. So basically that's what we're gonna spend most of today talking about, this idea of recursion. We're going to go through lots of examples of recursive programs, some which I think are kind of interesting in the way they behave. And we're going to talk a little bit about how, what's happening under the covers with recursion, just so you get a feel for what's going on at a more basic level. Okay, so we're going to first do the Unix tip of the day and the Eclipse tip of the day, and then we're going to talk about recursion, and hopefully get the little joke there. All right, and that's hilarious. Okay. First things first, so here's the Unix tip of the day. Oh, by the way, I'm trying something different with the lighting here. I don't know if you can tell. It's now, I'm trying to do a high contrast thing, and I still don't know where the lights are for this one. But anyway, I'm trying to do more of a high contrast thing so that it allows us the video to see it. The video last week just did not come out right, so I'm trying this. Hopefully it'll be a little better on the video. We'll see. Okay, so there's a couple things you may want to do with your program output. Okay, for a number of assignments this term, what we're going to do is we will give you output that is what we expect, right? Like an output of a program, and we expect it to be exactly this. And then you might want to check your output against that. Now, we already do this in the provide script. I already do this for the examples we give you. But later we'll have more examples with with the actual output that we'll provide to you as the assignment goes along. Here's what you can do. Okay, you can do this thing called piping to a file, right? Which is kind of cool. All right, let's see. There we go. What that means is, let's say, actually, let's go to, let's say I'm going to my lab 2 example here. If I have my Peanuts 5K and I run the file, notice that it actually prints out the results just like you would think. That's the output of the file. If I wanted to save that output to a file, all I have to do is type Peanuts 5K, the greater than, to say, hey, put it in this file, right? And then some file name. So I can say Peanuts output.txt, and it does it for me. It doesn't put anything on the screen. It just says, fine, everything that I put out output will go into Peanuts output. At least anything that's not an C error statement. The other statements will go out to that. Okay? And then if I do less on Peanuts output.txt, well, guess what? There's the file for you. And it's just a regular old file. Okay? And you can go through it and you can look at it and whatever. And so it's a nice way to save the output of your file to the thing. Yep, right.
For the provide,
Yeah.
If you want to pipe that output, but you need to enter yes partway through, is that?
If you want to pipe the output, let me think about this. That's a good question. If you want to pipe the output.
It just stopped because it was waiting for you to hit yes.
Yeah, you could still type yes, like it still asked you. You could still type yes, and it should come out. There may be a way to, I believe there's a way to actually pipe it to the output and to a file, and I forget the command for that right now. But if you remind me, I'll look it up. Yeah, Alex?
How is this different from like the vertical pipe?
Yeah, that's a good question. The vertical pipe says, here's the output that I want to send to another program. Okay, this output with the output with the greater than says send it to a file. If I did something like this, peanuts 5K, and then I was going to talk about this one a little later, but that's the pipe symbol, right? It's a vertical line. If I said do that and then count the words like WC, it'll actually run it through and say the output goes into the file or the command WC, and then it says, hey, the output had, I think it says 26 lines, 66, yeah, 26 lines, 66 words, 413 characters. So that's the difference there. Yeah, and this is a whole, like, you can go down the rabbit hole very quickly with this piping thing, but it's that's the basics of it. Okay. All right. So now let's say that I gave you some output. Okay. Let's say that I made you write a program that was Jack and Jill came up a hill or walked up a hill, right? That, you know that nursery rhyme? Jack and Jill climbed up a hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after. Let's say I made you write a program that output that, and you screwed something up, right? And instead of saying Jack and Jill climbed up a hill, you ended up saying Jill and Jack climbed up a hill, and you wanted to compare it to the output. If you have the output, like this happens to be Jack and Jill.txt. I also happen to have Jill and Jack.txt, which is exactly the opposite. Jill and Jack climbed up a hill. Now notice, the first line of the top one says Jack and Jill climbed up a hill. The first line of the bottom one says Jill and Jack climbed up a hill. Those are different, right? But what about the second line? To fetch a pail of water is exactly the same as the second line in the other one, to fetch a pail of water. See how that works? There's a program called diff, which says, show me the differences between two files. And it does so on a line-by-line basis. So watch this. If I type diff, Jack and Jill.txt, and then Jill and Jack.txt, right? What prints out is this kind of, looks like a weird kind of code, but it says, hey, on line 1, at line 1, character 1, there was a difference. The file that you typed first said Jack and Jill climbed up a hill. The file that you typed second said Jill and Jack climbed up a hill. And it will tell you the differences on there. It'll show you the differences, right? Notice the second line does not get picked up because it's the same. And then the third line, it says between the third line, I guess it's the third line and the fourth line, character 3, it says these are the differences there. And then these are the differences. These are the ones in the first file. These are the ones in the second file. Right now, this might not make much, like, you might not care about this right now, but when I start giving you more output that you can test against your own programs, this will become much more important. Okay? So that's that. Questions on that? No? Okay. Yeah, Alex?
Will you then be giving us like ideal output files?
Yes, I'll be giving you not just ideal output files, but exact output, like the output that we will grade on. Like the output should be identical. And if it's off by like a carriage return, diff will say, hey, these two lines are different by this, and that means it's different. So you've actually used it in the provide script, although you didn't know you were using it. But that's the way that works. Okay. Other questions on this? All right. Like I said, this will become more important as we go along. All right. The Eclipse tip of the day. So I keep hearing some grumblings. Not really. You guys say, hey, do we have to do this every time we set up a project? Link your folder and then change the Clang thing and all that? Well, I looked into it, and there is a way to make your program make Eclipse use Clang without typing that Clang business in. So this will save you a couple steps if you want. I'm not going to go through much detail except to show you that it's possible. In your home directory, you're going to create two what's called symbolic links that are going to say, hey, pretend that when I type GCC, actually run Clang, right? And when I run G++, actually run Clang++. That's what you're going to actually do. This is on the slide, so you don't need to write this down now. Once you do that, Then there's one other thing you have to do in Eclipse. You actually have to go to a certain preference file, and you can read this, but it's basically you go to this preference file, or this preferences window, and you change the path. Now the path says, hey, here's where you find all my files. And if you add the path to those two files I just showed you in, then it will forevermore use Clang instead of GCC, or Clang++ instead of G++. So you don't have to actually do that anymore. So if you want to use Clang, you can set it up this way, follow the instructions, they're on the slide, and you will only have to do that one step of linking your folders for every project. It just saves you a couple steps. Okay, questions on that? Again, I don't want to necessarily spend a lot of time going through the details of that. That's that. Okay. All right, enough with the Eclipse tip of the day. Let's move on to recursion. Anybody ever typed recursion into Google? Google says, did you mean recursion? Right? When I actually type recursion. So Google's made up a bunch of like nerdy engineers, right? And well, they are, and it's great as far as I'm concerned. Anyway, they put this nerdy joke in here that normally this says, obviously, did you mean something else? But this time it says, do you mean recursion when you type recursion? Because that's the whole idea of recursion, is like self-referential behavior, right? And up here I put, to understand recursion, you must understand recursion, right? And these are all like little jokes about what are we talking about when we're talking about recursion? And recursion is a very interesting mathematical property that says a function can refer to itself in a way such that it doesn't break down and like run off into infinity, right? There's these like this idea that we'll have to talk about over the next like hour or so about how that actually happens. Okay, and it turns out, and at the end of the lab, I put a little advanced reading on recursion in programming. And it's back when programming languages were first being like written, the first ones either didn't have the ability to do recursion, or people thought, we don't want to do recursion. It's like too much work and we don't want to bother with it. And I suppose cooler heads prevailed to allow us to do this recursion thing, but at one point it wasn't even really part of computer science because people hadn't thought that it made sense to do it. However, it does. Okay? Here is our first simple example of recursion, okay? This is a stupid example. You would never want to do this. This example says int main, and then main calls main, and this would actually fail and crash eventually, actually probably very quickly, because what happens is we go into main, and then we call itself, and all we're doing is starting the program counter, or changing where we are, the next line in the program, to the same line here. Because it says call main. Oh, OK, I'll set everything up. Call main, which is a regular function. Well, it's not a regular function, but it's a function. And then do it again, and do it again, and do it again, and do it again. And there is no way of stopping this. Right? If you did this, your program would just crash. And it would probably segfault. Or it may say something like stack overflow, which is really what's going on. OK? Remember the other day we talked about the fact that when you call a function, there's a stack that's part of your function that saves the current state of the function you're calling from. Remember that? That's exactly what would go on here. Main would call main, and then the first time it would say, OK, save where I am, call main. Oh, save where I am, call main. Save where I am, call main forever. Right? But that is a recursive program. It's a terrible one, but it is a recursive program. OK? All right. When we're talking about recursion, we can use examples in real life of solving a problem recursively. Okay? For instance, how to solve a jigsaw puzzle recursively. All right? Is the puzzle finished? Stop. Right? If you look at the puzzle and all the pieces are there and in the right place, you're done with the puzzle. Okay? I know it sounds silly, but that's really kind of, if someone said solve this puzzle and you walked up to it and all the pieces are there, you'd go, I'm done. Right? And that's like the first step. This step is important because if we forget to check if the puzzle's finished, we're going to keep trying to like do this forever. Right? So that's a key part of recursion. All right, the second thing is find a correct puzzle piece and place it. Now, the devil's in the details here, right? My girlfriend had a puzzle she was working on for like 8 months. Took up our table in the dining room for like 8 months, right? And she finally finished it, and guess what? One missing piece. Can't find it anywhere. And we don't have any pets to eat them either, so it's got to be somewhere, or it just missed it in the box. But anyway, I saw a puzzle once. It was, I think it was the hardest puzzle ever. It was a puzzle where they took a picture of puzzle pieces, right? And then each piece was like part of a picture of a puzzle piece, and it was horrible. Yeah, I'm not a fan of like doing it. But anyway, so you find a correct puzzle piece and you place it in there, and then what do? You solve the puzzle again. You start over and you ask the same question. Am I done yet? Right? And nope, right? I mean, I guess my girlfriend's still stuck on this one. Find a correct puzzle piece and place it, right? Because she's looking around the house still and it's not done, right? But the point is that this is a recursive algorithm because now we can define the problem in terms of itself. We can say solve the puzzle. Oh, okay, that means go back up here. Now, this can also be an iterative approach. Obviously, you could have a loop here, and you could say while the puzzle's not done, find a correct puzzle piece, right? And it's that's not recursive. That would just be an actual loop. Turns out you can always convert recursive programs into a looping program. Recursion is never absolutely necessary, as far as I know. There might be some really obscure reason why recursion is necessary, but I don't believe there is. And the big question is, why do we do this? Well, sometimes it actually looks a lot more like it's actually more beautiful in the kind of a esoteric sense, right? And the answer just jumps right out of you. What are we doing? We're finding correct puzzle pieces, and we're repeating a process, right? Because it's so simple there. Okay. Here's in general how we're going to solve these recursive programs. Okay? We have to check for what we call the base case. That's the part that says, is the puzzle complete? That's the part where you say, I'd better check and see if I'm done with this problem yet. Okay, that's called the base case. If you are done, you return, right? You return from the function. Many times you return a value because you're trying to solve and get some value, and you have to return the value back up to the original function. But that's the first thing we do. Then you work towards the base case. Now, working towards the base case means doing whatever calculations you need to do and then getting to where you're actually making the problem smaller by some measure of smaller. Okay, that's going to be working towards the base case. And then finally, we're going to be doing this recursive call, and that's the third thing. So check for the base case, work towards the solution to the problem, call yourself. End of story. Those are the three things that you're going to be doing in recursive programs. Okay? Let's start out with some very easy ones. You can get some very advanced ones, but let's start out with some pretty easy ones here. Okay? I see some people still writing. Remember, these are on the slides, or are online. Okay. How are we going to count recursively from some number n down to 0? In other words, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, we're done. I propose that this is the way we would do it. We check the base case. When do we stop when we're counting down from 10 or from anything? When we get to 0. It's actually, in our case, it's going to be when we get to -1, because we want to print out 0. But I guess I didn't really say that. But in this case, is n less than 0? This is checking the base case, right? If it is, we're done. We've counted down. We're done. And that's the base case. Then you actually say the number n, right? If we're counting down from 10, first you check, is 10 less than 0? No, 10, right? You say it. You print it out to the screen in the case that we're going to do, or that's what we're going to do. Okay? That's actually kind of working towards the base case. Not quite. I mean, we'll also need to actually decrement n, right? You need to say, hey, I've done 10, now I'm going to do 9. Okay? And then the countdown from n minus 1, that's when we say, look, count down. We are counting down. Count down is the recursive part of it. We count down from n minus 1. Okay. Everybody get the idea? There's check the base case, work towards problem, do the same thing again. That's all recursion is. Okay. All right. Here's what it looks like in C++. All right. Let you take a look at this for a second. Does it make sense what we're doing here? See if we're following our rules. If count is less than 0, return. We're done. That's checking the base case. Print out, basically see out what our number is, and then a little return, because we're going to print it to the screen, right? And then count down, count minus 1. That's the part where really we're working towards the answer, count down minus 1, n minus 1, or count minus 1, and we're calling countdown again, the same function. In our main function, we just need to say count down 10, and it does the rest for us, right? We have checked the base case. When we get to 0, so the program will stop. And I put in here, unless we try to count down with too large a number. What if I tried to count down from 10 billion? Besides taking forever, why might this program crash? Yeah?
Stack Overflow.
Stack Overflow, right? Every time it calls this, notice that, and this is the important part. OK, this is what we have to kind of understand here. Let's write down what's going on from countdown 4, let's say, right? Countdown, I'll start making it just CD to abbreviate. Countdown 4, OK? If instead of 10 I said 4 here, what this would do is this would call, it would start running the program. It would say if count is less than 0. Is count less than 0? No. OK, print out the number, right? So it's going to say 4. OK, and then it's going to say count down, count minus 1. So what's going to happen is we're going to say count down and then 3. And then in this one, where does it go? What's the next thing that it does in the program? Where does it go next? Like, where's the next line? When I say count down 3, what's the next line that's executed? If count is less than 0. And now the count is a new number, which is 3. You got to keep track of it. Like the count changes, right? Countdown 3 is now because it's now in this again, and it says is count less than 0, which it's not. So we go to this line, see out count, which is now 3, and it's going to print 3 like that. And then what's it going to do? I'm going through this like kind of one line at a time, and I'm not trying to insult your intelligence, but it's going to count down 2. Go back up to if count is less than 0. It's not. Print out the number. Count down 1. Right? Go back up. Same thing. We're going to count down 1. So is count less than 0? No. Print out 1. Yeah, Charlie.
If we know how much memory that each time we call countdown is going to take up in the stack,
Yep.
and we know how much stack memory is available to us,
Yep.
is there a way, can we calculate how many iterations of a recursive function we can compute before?
Yeah, the question is, can we compute how many of these are we going to do before we get Stack Overflow? Probably. It wouldn't be an easy calculation because it depends on the compiler you're using. It depends on the operating system you're using. It depends on a lot of those things. It depends on how you set up your operating system to how much stack space you have. But sure, you could, right? You could, and you could try it and keep incrementing this, double it every time until it crashes, then go back. And you could figure out, hey, how close you are. It'd be an interesting calculation, but you could do that. OK, countdown 1 gets called. Countdown 0 gets called. 0 is not less than 0, so it prints out 0. And then finally, countdown 0 calls countdown -1. Right? Countdown -1 says if count is less than 0, we're done. Right? We've made it. Return. Does the program end right here? It does not, right? What happens is it returns to this function. And this function's next line is like no other. It's done. When it gets to here, it just returns on its own, right? Because it's done with the function. This one returns to here, which returns to here, which returns to here, which returns to here, which returns to main. And then main finishes, and we're done. So there's a lot of like whoop, 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 returning here that's going on. OK? You wouldn't really want to do this in real life. You'd want to make a countdown counter that's iterative. You'd want to just make a for loop or whatever, right? That's how you'd really want to do it. But I'm showing you how recursion works so that you get the idea of it. But this is the important part, right? We'll see lots of examples of this today that make it more interesting. Question?
I'm still puzzled about the idea of making it count down by too much. I mean, wouldn't that just make it not count?
Making it count down by too much. What do you mean?
All right.
Oh, let's say I put instead of countdown 10, I put 10 million. Right? Well, every time we call one of these functions, this gets saved, and our memory runs out.
Sorry, I
That's all.
misunderstood.
Yeah, that's all. Okay. All right. So that's how we count down using recursion. What if we tried to count up using recursion? Could we do the same sort of thing? Ah, what's the base case for counting up? What is it? Well, yeah, I mean the amount of memory. I don't know, Charlie. What do you think?
If the count is equal to the number that you want to count to.
If the count is equal to the number, can we do it just using one variable like this? Yeah. See, if we tried to do this and we said if count is greater than, what would we put in this greater than here? Right? I mean, I think I have the next slide actually kind of demonstrates what's going on here. Yeah. So we could count up, right? And we could say, hey, if count is greater than some number, but that number is going to be, like, what are you going to increase it? I guess this could be, it doesn't make much sense. Yeah.
So what if instead you see out it after the recursion?
Oh, I like that. That's 2 slides from now. So you are jumping the gun just a little bit, but that's awesome. Okay, what's your name? Morgan. Have I seen you in lab? You probably got lab at 4:30 on Tuesdays, don't you? Yep. Yeah, I thought so. That's the only lab I really haven't been able to be to. I went there once, just once, briefly. I don't know if you were in there. Anyway. Okay, Morgan was it? Yeah, okay. What Morgan said was right. Pause for 2 slides and we'll see what he's talking about, if you didn't get what he's talking about. Morgan, I'll let you explain what you mean in 1 second. There are a couple different solutions. The one Morgan gave is actually pretty cool. There's a couple solutions, though, one of which is to say, look, there's nothing saying we have to have just one variable. We could do this like this. We could say some number to count up at, but let's start that at 0, because we're going to count up from 0, and then the maximum number, and then just pass this maximum each time, and that's where our base case is going to be. We're going to check that maximum, right? So we could do this. If count is equal to max plus 1, return. I guess I could have said greater than max, return, right? See out count, and then count up with count plus 1 and max, and just pass max along. And every time it knows to use max, right? That would work just fine. This is kind of ugly, though. If you're saying count up to 10, and I say, well, what you have to do is you have to actually put the 0 in there as well. It's just because I'm not a very good programmer, right? So you don't want to do that. You don't want to say, tell somebody to count up. Now, what we could do is we could make what we call a helper function that said this could be count up helper. And we could make a count up function that just automatically calls it with 0 and returns it. We'll get to another example of that in a little bit. But this is one way. This is not a bad solution, actually, because this is actually more robust, right? We could now count up starting from some other number. If we said count up 4 to 10, then it would go 4, 5, 6, 7, 8, 9, 10. Right? So that's kind of nice. I mean, this is actually a more robust example, but it's not quite the same. All right. Now, Morgan in the back, stealing my thunder, says do this. Morgan, want to explain what you're talking about?
So you go down the function call. You haven't actually done anything every time you go down the function, and then only when you're coming back up the function calls do you print it out.
Yeah. Exactly. So let me see if this is what you're saying. Let's just go through this for count up to 3. I'll make you do 4 next time. Count up to 3, right? Let's follow along what's going on here. And all I've done, by the way, is I've swapped these 2 lines. It's exactly the same program. All I've done is swap these 2 lines like that, right? And this is now saying count up, count minus 1, and then afterwards it's printing that. The reason I'm going through it in this detail is so you get it right in your brain about what's going on. OK, count up 3. OK, it calls count up 3. If count is less than 0, it's not. What's the next thing that happens? What's that? It calls itself again. Count up 2. Calls itself with count minus 1. Have we printed anything yet? No, we have not. Let's go see what happens when we do count up 2. Count up 2, is count less than 0? No. Count up 1. Count up 1, right? And then count up 1 does the exact same thing, it says not less than 0, calls count up 0. Count up 0, count up 0, it's not less than 0, it calls count up -1. All right. Count up -1 says if count is less than 0, return. we're done, right? So this one's going to return to here. Where in COUNTUP are we at this point? Where are we? The printing part. We have now exited out of COUNTUP -1, come back to COUNTUP 0, which just as far as it was concerned said, OK, COUNTUP -1, now print out my number. Well, what's the number that's in COUNTUP 0? 0. And then the next line is the end, so it returns. So it goes back up to 1. 1 just said do the COUNTUP -1, and now it says print my number. What number is it? 1, all right? And do you see how that continues along? COUNTUP 1, and then it gets to COUNTUP 2, and it prints 2, and it gets to COUNTUP 3, and it prints 3, and then that's it. We have counted up using a single variable. Ah, interesting, huh? We've just changed when we've done the printing out of this, right? Now, let's step back a second. Is it worth, like, what's the worth of going through this whole thing and seeing, oh, I can figure out a fancy way to count up, right? Well, it's just to get through your head, hey, when you call a function, the next line is after that function is done. And by swapping the order here, we can actually change the output based on that analysis. Okay, that's really all I'm so worried about. Okay, it's pretty clever in this sense. I mean, I call it clever because, hey, you could it just changed one line, right? Thank you, Morgan, for being clever. Now, if you're going to tell me you read the slides ahead of time, you didn't, though. I'm sure you didn't. Okay, all right. So those were kind of the basic idea of recursion. Again, recursion is not something that you should always try to make recursive programs, right? I mean, it does look nice. It's a very clever solution. A lot of you'll hear clever thrown around a lot when you're talking about doing recursion, because it is kind of interesting. Like, you can come up with these cool ways of writing very little code that does a lot of stuff, right? The other uses of recursion, we're going to see some other examples of numerical kind of things we can do with recursion. But there's other uses of recursion. If you're trying to walk a linked list, right? Isn't that a very recursive process? Look at your node. If you're at the node you want, stop. That's kind of the base case. If you're not at the node, repeat the process with your next. It's a very recursive idea, right? I wouldn't want you to do that, because what if I give you a list of 1 billion elements, right? You're going to kind of run into this whole Stack Overflow problem, and it's just not that great. It's a very pretty solution, right? And people, if you've ever studied Lisp or Scheme or other kinds of languages like that, they love recursive solutions. It's all about recursion, right? Now, those languages actually have a way to kind of change the recursion so that it's not, so that it doesn't affect the stack. There's this thing called tail recursion. Tail recursion, which you can look up. I put a little a note at the end of the presentation about that you can look up tail recursion. But that's a way to do this fun stuff and then make it so that it doesn't kill your stack. It's built into some compilers, generally not C or C++ compilers, unfortunately. Okay, all right. So let's look at a couple other examples here. Okay, we're going to look at these other examples of recursion. I will have the C code for all of them, and we're going to go through them in a little bit of detail here, so you kind of get the idea of what's going on. Okay. First, we're going to look at b raised to the power of n. Okay. If I want to do 2 raised to the 4th power, can somebody kind of walk me through why you can do that as a recursive? So, why this might be ripe for recursion? Maggie.
So that's really saying 2 times 2 cubed.
Yeah, right? Perfect. And then what's this saying?
2 times 2 times 2 squared.
Right, and then 2 times 2 times 2 to the 1st, and then 2 times 2 times 2 times 2 to the 0, or whatever, right? So yeah, it's exactly it. If you can break the problem down such that you can make it a smaller variety of the same problem, you've all of a sudden got a recursive solution. Okay? So this code is actually not too bad for b raised to the n power. I'm using doubles here instead of floats. You could use floats. You could use integers if you wanted to. Right? But let's look at it. Pretty simple, huh? Right? It's really simple. First, you check and see if you're less than or equal to 0. Right? If you're less than or equal, if you're less than 0, then you're kind of in trouble for this algorithm, because even though you can do 2 to the negative 3, well, you can't do that in this recursive algorithm because powers go kind of in both directions. You can't really do it using this one. So you'd probably have to what we call throw an exception or seg fault, or well, you wouldn't want a seg fault, but return or whatever and say I can't do it. But let's pretend we're doing just positive numbers here. Does this make sense? If the n is less than 0 or less than or equal to 0, basically return 1, because anything raised to the 0 power is 1. So it works for our base case, definitely. Right? Now this is the interesting part. This says return b, which is the number we're trying to raise, times the power of b n minus 1. This is exactly what Maggie was saying, and this is how it's going to work. Let's walk through just a couple. Let's do 2 to the third. Why not? 2 raised to the third power. OK, so we're going to call power 2, 3. OK, and n is 2, and b is 2, and n is 3. OK, is n less than or equal to 0? No. What do we do then? We return. We do the else statement. Return b. So we're going to return. This is the important part. Return. Right? We're going to say b times the power of b to the n minus 1. In this case, b is still going to be 2, and n minus 1 is now going to be 2. So we're going to return b times power of 2, 2. I'll just change it right there. 2, 2. This part's the interesting part. Okay, you're returning to this value, whatever the result is of b times the thing. Yeah?
On the very
Change this one too.
low level,
Yeah.
is also how multiplication is implemented from addition.
On a very low level, is this how multiplication is? It could be. Yeah, you could implement multiplication by saying a recursive function of saying add until I reach the, what would it be? Until I've done it and x number of times. Yes, you absolutely could. Well, yeah, not necessarily the best way, but definitely a very low, low level, certainly a recursive way. Absolutely. Yep. OK, so now this one's going to now return 2. Now, this pow 2, 2 is going to do what? It's going to check for 0. It's not less than 0. So it's going to return pow of b. It's going to return, it's going to return b 2 times. So this is going to return 2 times the power of, same thing, 2, 1 now, because we're decrementing by 1. This one, return 2 times 2, 0. Is it equal to 0? Now, our n is now equal to, n is equal to 0. So this is going to return 1. Sorry, it's hard to see if you're in the back there. This is returning 1. So now let's add this up and see if it works. 1 returns to here. This says return 2 times 1. 2 times 1 is 2. This then returns, this is now 2. This says return 2 times 2. Right? This becomes 2. This one says return 2 times 4. This one says, and that's it. 2 times 4 gets returned up to our calling function. 2 times 4 is 8. There's our result. OK, do you see how that return actually passes the information back up and each time applies the answer? Yeah, this is the kind of stuff that I want you to kind of get in your brains about how this works. OK? All right. OK, let's move on. Any questions about power? If you wanted to try to figure it out for negatives too, you could. Slightly different idea. Probably be dividing instead of multiplying. Okay. All right. Let's look at the factorial function. Now, this is really the same idea, isn't it? I mean, factorial, remember factorial is whatever number times the number minus 1 times the number minus 1 times the number minus 1 all the way down to 1. Right? Here's our nice, quick, easy, dirty factorial function. Right? If n is less than or equal to 1, return 1. That's our base case. Return n times factorial n minus 1. I'm not going to go through the details of this again, because it's exactly the same idea. Right? Factorial of 5, right, returns 5 times factorial of 4. Factorial of 4 returns 4 times factorial of 3, et cetera, and then in the end you've got 5 times 4 times 3 times 2 times 1 returned all the way back up. The bottom returns 1, and then the next one up returns 2 times 1, the next one up returns 3 times 2 times 1, then 4 times 2 times 2 times 1, then 5 times 4 times 2 times 2 times 1, and you're done. Questions on that? No, pretty simple. I wanted to show you that it's not that much harder, the iterative piece, right? I mean, you could do this one iteratively really easily. Like if I said at the beginning of comp 11, come up with a function that said do a factorial, you could do it using probably either a for loop or a while loop. For loop's a good choice in this case, right? First of all, return 1 if it's equal to 1, right? Otherwise, you've got this temporary result here, right? Otherwise, go from n down to 1 before, and then return it. You can probably actually take out one line in this. I'm not sure the if business is even necessary in that one. But that's the basic idea. Okay? All right. Questions on factorial? How that's done recursively and iteratively? Again, compilers can almost always take, well, not always, but compilers can a lot of times take this, turn it into this, and then you actually don't have any stack things to worry about anymore. It's not always the case. This tail recursion is the one that makes it interesting. Okay? All right, let's look at Fibonacci. Who remembers what the Fibonacci sequence is? What's Fibonacci sequence?
Sum of the previous 2 terms.
Sum of the previous 2 terms is the next term. Okay, so Fibonacci sequence, right? This guy Fibonacci, I guess, developed it. Comes up a lot in the natural sciences, like flowers and things have, and they tend to branch out using like this pattern, right? Supposedly, like seashells and things have these interesting like Fibonacci patterns in them. It's kind of an interesting idea. But here's how it's defined. Okay, you start out with 0 and you start out with 1 as being already defined. Okay, this is Fibonacci of 0 equals 0. Fibonacci of 1 equals 1. And then Fibonacci of 2 equals 0 plus 1. It's the previous 2 numbers added together, which is just 1 again. All right? Fibonacci of 3 equals the previous 2. Right? So it goes 0, 1, 1, 2. Fibonacci of 4 equals 2 plus 1 is 3. Right? So far it's kind of boring. Right? And then Fibonacci of 5 is where it starts to get a little interesting. 5. Fibonacci of 6 is 8, and so on and so on. So you see the pattern. That's the Fibonacci sequence. You've probably seen it in a math class somewhere or something else. Maybe in a programming class before. This is the Fibonacci function that we're going to start with. Okay? This is one of those, this is like a classic example of recursion. And it's shown in a lot of different classes, right? And it's very beautiful, right? Why is it very beautiful? It's 3 lines long, 2 of which are just like if statements, right? First, if it's n equals 0, return 0. If it's n equals 1, return 1. And otherwise, just return the Fibonacci of the previous one plus the Fibonacci of the second previous one. Beautiful. Terrible, right? Why is this terrible? Yeah, go ahead. Oh, sorry, did you say why it was terrible? No, go ahead, Alex. Yeah, let's see. Not only that, but, well, let's walk through this. Let's do the Fibonacci of 5. Let's see if I can actually fit this on the board, right? Fibonacci of 5. OK. Is n equal to 0 or n equal to 1? No. So what am I going to do? I'm going to call Fibonacci 4 and Fibonacci 3. And I'm going to do it like this. Fibonacci of 4, right, plus Fibonacci of 3. OK. Now we've just broken the problem down, but we've gone whoop in 2 different directions. What's Fibonacci of 4 going to do? Yeah, it's going to call Fibonacci of 3 plus Fibonacci of 2, right? And it's going to return that, actually, return, right? So this should say return that and that, right? This one's going to return Fibonacci of 3 plus Fibonacci of 2. This one's going to return Fibonacci of 2 return Fibonacci of 2 plus Fibonacci of 1, right? Okay. What's Fibonacci of 3 going to do? Right? Return Fibonacci of 2 plus Fibonacci of 1, right? Let's go this way. What's Fibonacci of 2 going to do? Right? Return Fibonacci, I can't fit it on the board actually. Fibonacci of 1 plus Fibonacci of 0. What's Fibonacci of 1 going to return? 1. What's Fibonacci of 0 going to return? 0. So I barely fit this one on here. So this is going to return 1 plus 0, right? Same thing here. Return fib 1 plus fib 0, right? Which is going to be returning 1. Oh boy, and then we still have that side to do. So you see how this is like expanding the problem? Not only is it expanding the problem, what have we done a whole bunch of times? We've actually done Fibonacci of 2 here. We did it here. We did it here. We've repeated work, right? If we've done the work already, why should we repeat it? I don't care if it's beautiful. This is terrible. Right? This is like the beauty of recursion. Yeah, it's terrible because of this expansion. Remember how I said the other day that we want to avoid exponential algorithms? Well, this is another example of an exponential algorithm, right? We're breaking the problem down. We will eventually solve the problem, but in doing so, it's an explosion of other work that we don't want to do. Okay, so not a good way to do it. Beautiful, not so great. There is a better way to do the Fibonacci series using recursion. It's a little bit uglier, but it's so much better, right? Here's a better way to do it. Okay, while I'm erasing, take a look at these two functions. This is the case where I said, let's use a little helper function to do a little extra work for us, and let's pass along some information. If we've already calculated something, pass it along so that we don't have to calculate it again. Don't do Fibonacci of 2 16 times because you think it's beautiful, right? Do it this way and see what it. So let's look at what fib helper actually does. Okay? Fib helper is still counting down, isn't it? It's still going like, from the number of the Fibonacci things we're trying to find, down by 1 each time. But it's passing along some extra data here. Okay? Let's see if we can look at what fib helper of actually, we'll do 5 again. Fib helper, I'll abbreviate. Fib helper of 5, 0, and 1. Now this 5 is going to be our n, right? 0 is going to be what we call p0, which is the previous value, and then p1, which is the one before that. Okay? Here's what it does. Very similar. If n equals 1, we're going to be done. That's our base case. Otherwise, we actually return fib helper. I should put the return in there. Return fib helper of n minus 1 for p1, which was this one, and then p0 plus p1. Haha. Now we are saying, OK, let's keep the information here, and let's pass it on to the next iteration of the next recursion of the fib helper. Fib helper 411. OK, it says is 4 greater than equal to 1. It's not. So it's going to return fib helper of 3. This one's going to be p1 is going to go to where it's going to be returned for this as the second. It's going to call as the second parameter. And then 1 plus 1, 2. Aha. See how this is now kind of doing the Fibonacci sequence kind of in these two variables, if those are the last two sequences? OK. Fib helper 3 says, nope, it's not 1. This is going to return fib helper of 2, 2, 3. I'm gonna do the board up here. This is gonna return fib helper of 1, 3, 5. If n equals 1, what's going to get returned? The P1, right? In this case, P1 is this one. So it's not 3, it's actually this one. So this returns 5. 5 gets returned back to here, which said return whatever that one returns. So 5 gets returned to here, and 5 gets returned to here, and 5 gets returned to here, and then it's the final result is 5. That's actually much more clever in terms of being able to calculate your Fibonacci sequence without doing all this exponential work. You do it once. Okay? It took me a couple times to get my brain around what was really going on here. But once you see it, you go, oh, I get it. Okay, I see what's going on. And I'm calling this fib helper. This goes back to that thing I mentioned earlier. You don't want to say to your customer who's using your function, calculate the Fibonacci sequence, but don't forget when you first call it to make it a 0 and a 1 here. Right? You don't want to do that. That's why we have the original, we call it Fibonacci, saying, just give me the Fibonacci of 5. And in here, we call the fib helper with our first set of values, 0 and 1. Okay? And then it actually works. Kind of neat. Kind of a neat recursion when it comes down to it. Questions on that? Okay, that's a better way of doing it. And again, I'm not necessarily expecting you to be able to come up with this stuff out of your brain, but just understand that you can sometimes rework the problem to pass more data through a recursive function and save yourself a lot of work. Okay? All right. Greatest common denominator. Here's another one. It's an interesting recursive function. All right, let's bring ourselves back to 5th grade or 4th grade when we learned about greatest common divisors. GCD, did I just call it that? Greatest common divisor, right? Or divisor, I never know. Divisor? Divisor, yeah. What's that? Divisor, I would call it divisor. So here's the idea here. The greatest common divisor. Okay, we've got a couple numbers. Let's say the greatest common divisor, GCD of 12 and 8. All right, what's the largest number that divides both 12 and 8? 4, right? Okay, so that's what we want our answer to be. There are a couple different ways to do this. Okay? The straightforward approach is to say, okay, well, anybody want to walk me through what I might call a brute force way of doing this? Alex, you just answered. Go ahead.
Try each number from 1 to the smaller of x or y, and see if it's a factor of both, and then store it somewhere if it is, and then when you get to the end.
Well, okay, so you're saying go from 1 up to the smallest of these two, and then check and see, and if you get to the point where you've got 2 that's something that divides into both of these, store it, and then go on. You can use a stack for that, maybe. I don't know. Use something like that. What might be a slightly better way to do it?
You could also start at the smaller value and then return the first one.
Go down instead of up, right? That's exactly right? So in this case, go boop, boop, down. And so we might start with 8. And we could say, does 8 go into 12 evenly? Nathan?
Well, assuming when obviously we know that 8 doesn't. So
Right.
if that happens, it might be best to immediately divide that in 2 because you know that 7, 6, or 5 can't do it.
That's an interesting idea. You might want to divide this by 2. I'm not sure that pattern continues as long as you think it does. For bigger numbers, like just dividing by, I'm not sure the dividing by 2 works every time. It may, but there's actually a slightly better way than that, believe it or not. But let's stick with this one for right now, and let's just see what that might look like in a recursive way, going one number by at a time. And by the way, if you check 8 goes into 12 evenly and it's not, then you check 7, then 6, then 5 all the way down. That's like the brute force method. Okay? All right, before we even do that, did anyone know in C++ how we find out if something divides into something, right? The modulo, not ampersand, but the percent, which is modulus. It's the percent symbol, right? And if we do 12% 8, all that's saying is, another word for that is the remainder. It's an integer division, and it gives us the remainder. So 12% 8 should be what? Not 0. 8 goes into 12 how many times? Once. How much the remainder? 4. So 12% 8 is 4. Okay? I always used to get this backwards, but I do this one out in my head, and then something like 8% 12 is what? Yeah, it's 8, right? Because 12 goes in 8 0 times. There's 8 left over, right? So any number modulus a bigger number just gives you the original number. All right, it's just the remainder though, right? 12 remainder 5 gives you what? 2, right? Because 5 goes into 12 twice. There's 2 left over. There's the answer. Okay, so this is how we're going to figure out whether or not we've got a number that goes into the other number. What's the modulus going to be if we know it divides evenly? 0, right? So the modulus we're going to look for is 0. Okay, so here's what we might do. We're going to come up with this function called tridivisor, and that's another helper-like function, right? And it says, fine, take 3 inputs, right? The 2 numbers we care about, and then some guess, g. Okay? And the guess, in this case, a good guess would be which one? You said it earlier. You said which one to go up to? The smaller of the 2, right? If you guessed the larger of the 2, it wouldn't matter. It would still work out just fine because you'd eventually get a bunch of like remainders that are that other number, and it would eventually devolve down to the lowest one. But you might as well start with the lowest one, because if you don't, well, then you've wasted some time. All right? This function doesn't actually care, as it turns out. But all you do is you check and you say, look, if the first number divided by the guess gives a remainder of 0, and the second number divided by the guess gives a remainder of 0, we return that number because it must be the greatest, if we're starting from the lowest of the 2 numbers we started with. Return that number. Otherwise, or else, return tridivisor m and then 1 less. So we would do 8, then 7, then 6, then 5, then 4, then 3, then 2, then 1. Well, actually, we would stop when we got to what? For 12 and 8. Stop when we got to 4, because 12 remainder 4 gives you 0, and 8 remainder 4 gives you 0, and that's when we would stop. Okay? But see, it is a recursive function because it's doing tridivisor again. Okay, so that's one way to do it. Now, Nathan actually brought up a very interesting point. He said, hey, there's probably a better way. Like the fact that 8 doesn't go into 12 means there's probably a number that's not just 1 less than 8. I'm not sure I buy that it's half, but there's another one that's very interesting. Isn't half the next number that would go into 8? Let's see, I guess it would. Yeah, I guess it would have to, yeah. So half would work in that case, yeah. Half would work in that case. So you could say instead of g minus 1, g divided by 2. The only issue is, I guess, what if it's odd, and what happens when you... Yeah, 9 and then 3. I mean, you do 9 and then 4 and a half, and then how do you do 4 and a half? You can't do anything. It only works with integers. Yeah?
Is it the remainder?
You actually do pass the remainders, it turns out. This is a very interesting way to do this. This is where it comes back to. Before we had Fibonacci, which was kind of ugly. The first attempt was ugly, and the second attempt was really beautiful. Or the first attempt was beautiful but not good. The second attempt was uglier but better. But this one's kind of the exact opposite. Yeah. So Senna, right? So Senna says we are going to return the greatest common divisor of the number we try to divide by, and then the remainder of the 2 numbers, the bigger one than the smaller one. This is actually the coolest algorithm. Okay, I'm not going to go into details about like why this actually works. It's like a 3 or 4 line proof. I have, if you go to this website here, you'll find out what they talk about it a little bit, but it's one of those things where I don't want to like sit here and do a whole bunch of math on the board and go, oh yeah, I kind of screwed up there, and you can read it and it'd probably be a little more clear than me doing it on the board. But this is it, as it turns out. This actually works much faster than the brute force method. And here's what's going on. Okay, let's try this with greatest common divisor of 12 and 8, like before. Greatest common divisor of 12 and 8. Okay, if the second one, the 8 in this case, equals 0, we're going to return the first one. Okay, well, this is kind of interesting, all right, to start out with. If this one's 0, we're returning this one. Otherwise, we return the greatest common divisor of the second one, 8, and then the remainder of 12 and 8, which we already said was 4, correct? All right. This greatest common divisor says, OK, first of all, is 4 equal to 0? It's not. OK, so it's going to return the greatest common divisor of the 4, and then 8% 4, or 8 modulus 4, which is what? Jean-Marie says 0, which it is, right? And then this one now, this function says, oh, guess what? It is 4. I keep forgetting to do this. Return, like that. This one says, OK, the greatest common divisor of 4 and 0, well, y is equal to 0. Therefore, just return 4, right? And that returns here, and returns here, and returns here. And there's your answer. Ho-ho, pretty cool. Yeah?
So if you put in 8 and 12 in opposite order, do one more step.
Yeah, if you did 8 and 12 in the opposite direction, let's see if it's just one more step. All right? Let's see, 8 and 12. We're at 8 and 12. OK, so this is going to say is 12 equal to 0? It's not. Return 12, and then 8% 12, which we already said was 8, which you're right. It goes exactly into the one we just did. So it's exactly one more step. Yep, so you don't have to, you'd remove one step on that one. OK? Yeah, pretty cool. Let's see if it works for, prime numbers. Don't have any divisors, right? The greatest common divisor of 13 and 5. OK, 13 and 5. We'll use this formula here. Is 5 0? It's not. Return 5, greatest common divisor of 5, and 13 modulus 5 gives us a remainder of what? Gives us a remainder of 3, right? And then this one, greatest common divisor of 5 and 3. 3 is not equal to 0, so we're going to return the greatest common divisor of 3. And then 5 modulus 3, 2. Return greatest common divisor of 2. 3 and 2, 1. All right, let's see. It's not equal to 0 yet. Return greatest common divisor of 1 and 2 modulus 1. What's the remainder? 0, because 1 does divide into 2 equally. 0. Now we return, it is 0, so we return 1. 1, 1, 1, 1, 1, 1, 1. Guess what? The greatest common divisor of these two numbers is 1, which it is, because they're both prime, right? Whew. OK, so it works. All right? This one actually took a lot of work to get there, it seems. But you'll generally do it much many fewer times than before. And I like what you guys were saying about the divided by 2, but it makes it trickier, I think, in the end, because you got these weird half values and so forth. But that's that. OK, questions on this one? OK, that one's kind of a cool one. Yeah, Ben.
What if you had it checked to see if they were even?
Check to see the, oh, you mean right at the beginning?
Yeah.
Even doesn't necessarily mean, I mean, you could have the greatest common divisor of 25 and 15, right? They do have a greatest common divisor. But
What I mean is if you had a specific path for odds and evens.
Oh, I see. OK, so could you come up with some other way where you're checking, do a different path for odds and evens? Probably. Would it ever be better than this? I'm not sure in the end, like in the long term, it's worth doing two functions for it. Probably not. But there are definitely cases where, you know, if you had some function that said, check if these are prime first. First of all, you'd win what's called the Fields medal, which is like the best medal. Like, you know, if you could do that in real time, right? And then you'd also break all the internet security we have in the entire world. So if you could do that, that'd be a great way to do it. But you probably can't right now, right? So that might save you some time if you could do that, though. OK. All right. So let's look at one more here. OK. The last one I want to look at is palindrome. And I'm not going to let you peek at this quite yet. Is palindrome. I know you already peeked. All right. First of all, what's a palindrome? Somebody hasn't answered in a little while. Palindrome. Jean-Marie.
It's where it's going from the have a mirror image.
Ah, oh, I like that definition. Going from the middle out, you're going to have a mirror image. Yeah, that would work. That would work. Kind of. I mean, it's not really an image, but it's a mirror letters if you're doing letters. Yeah. Cam, what were you going to say? Spelled the same backwards or forwards, right? What's the classic one is Madam, I'm Adam, right? Without any like funny stuff in there, right? The punctuation, right? Madam, I'm Adam, going backwards, M-A-D-A-M, I-M-A-D-A-M. It's the same, right? There are people who create like entire books out of palindromes, right? I mean, it's one of those puzzle things people love and whatever. But the question is, can we write a recursive function? I propose that we can, because I just showed it to you, that actually checks and sees if a word is a palindrome with doing the recursive function relatively smoothly. Walk me through what we might do to figure out if this is a palindrome. Just it doesn't have to be recursive, just in general. Charlie, what do you think?
I was thinking, have a look at the first entry, like the first character, and then compare it to the last character, and if they're the same, then pass the same string, but without those characters.
I think I like that. I like that idea. Did you get what Charlie's saying? Right? You say, look at the first and the last, and if they are the same letter, we're good to go. Do the same thing, but this time do it on the smaller string, just lopping off the last character and the first character. Not bad. And does that work again? We can do this one. We can look at the A and the A here, same thing, and then we're just going to pass D, A, M, I, M, A, D, and same all the way down. Yeah, Miranda.
Could you also do this as like a stack?
Could you do it as a stack? I bet you could do it as a stack, yeah. Yeah, how would you do it with a stack?
Because it's just kind of like the same thing when we had the parentheses
Yeah.
thing the other day. So like the outsides are going to like work inward.
Yeah, it's a little tricky because, I mean, a stack, you probably could do it with a stack. I mean, like, you'd have to go from kind of both ends, maybe? I don't know, because if you do M, A, D, A, and then you get an M, what do you pop the other M? I mean, you're popping here. You have to know where the middle is, I guess.
You have to know the length, the total length.
Yeah, you'd have to know where the middle is, right? Pop and push until you get to the middle, and then start popping, and if they're all the same, then you're good to go. That would work. You'd have to be a little careful because odds versus evens. Like if you have an odd number versus an even number, then you have to know, oh, when do I start popping? But that's good. Alex, did you have a comment?
Yes.
What's that?
Would it be more effective to do it with a stack?
More effective? Well, you wait till you see my solution, then maybe we can figure that out. I'm not sure. More effective, probably if you were trying to do a book length one, maybe. Like if you had trillions of characters or billions of characters, then saying you'd run into the same stack issue if you're doing recursive. Yeah. Nathan, you had a comment?
You could, and if you look at both ends at once and start canceling out letters, then when you find that as long as it continues to match, and if your string length is either 0 or 1, you've created one.
Yeah, if your string length is either 0 or 1, you've definitely got a palindrome at the end. Because in this case, this happens to be an odd number 1. We would get to the I being in the middle, and it's the only thing left. Well, if it's the only thing left, it's got to be a palindrome because we checked everything on both sides. Good. So Sonny had a question?
Yeah, don't you know the length first, though?
You would have to know the length if you're trying to do you're trying to look at both ends, sure. In general you would. Yeah. But you see how this can be this is a breaking the problem down recursively. It's not too bad. Okay. Let's see. All right. Here's what I came up with. You might have come up with something different. First thing, check the base case. Don't forget to check your base case. If the length is less than 2, which is what Nathan was saying, return true. It means we are done. If we've got a length that's less than 2, a palindrome of either one character or no characters, it is a palindrome, right, by definition. Okay? Then check if the first and last character match. If they match, recursively check the rest of the string, which is exactly what Charlie was saying, right? Here's how we might do it in C++. It turns out you can refer to the individual characters of a string using this bracket notation, just like you would an array. Kind of nice. They've overloaded this bracket notation, right, to say that S0 is the first character, and S.length, which is what Susanna was saying, is the last character, right? Well, actually, that's not true. Length minus 1 is the last character, right? And then if you check those two, if they are equal, then you go ahead and I used a little function called erase. You could have done it, so there are other ways to do it. You could do a little for loop and get the middle characters, blah, blah, blah. There's a function called erase, which says go from the beginning to the beginning plus 1, and then erase from the end minus 1 to the end, and it just returns the string without those first and last characters. And then you return is palindrome, the new string you just came up with. Done, right? And if you ever get to a point where the two letters do not match, return false. Okay, kind of neat. Kind of neat. Okay. All right, questions on that one? Yeah.
If it returns true, will it pass? It will continue to pass the true back through again, and then when it gets that final return, it's going to break out of your statement. Or
Good question. Okay, so if you did is palindrome on this long one right here, right? It would have to go. It would go until it would say do the outside ones, then the next one, then the next one. If it ever got to one where it was false, it would immediately start returning back up the stack. So then you would get false being returned back all the way up. The only time you ever figure out if it's true is if you get all the way to the middle and it is true. Then it returns true all the way up the stack. Yeah, good. Okay, let's see what. Just curious. Let's see. The longest palindrome in English, because I bet other languages have palindromes as well. All right, palindrome. Let's see, long palindromes. Okay, longest palindromic word is the onomatopoetic trataratat, coined by James Joyce and Ulysses. It's a pretty good pedigree. Guinness Book of World Records gives a title to detartrated. Let's see, sorry, this is probably tiny for you guys. Hang on, let me put this down. There we go. Okay. Let's see. Where'd it go here? There we go. What happened to the, hang on. There it is. Okay, let's see. More English. 2 palindromic novels have been published. And of course, the title is also a palindrome, of course, right? And it is 58,795 letters. Whew, I bet it doesn't read very well. And there's Dr. Awkward and Olson, and also 31,954 words, which is a lot of words. 224-word poem, Damn It, I'm Mad, by Dimitri Martin. I would be too after doing a poem that way. There you go. Anyway, so then palindromes are, other sort of things. Computational theory. So palindromes are kind of cool, and you can come up with those. One last thing I do want to show you, which I showed the other class, and then somebody in this class, I think, said, hey, why didn't we show us this? It's because I didn't have it yet, I think. Let's see if I can find this. YouTube. I put this on YouTube. Let's see. Oh, I got to sign in. Hold on. Oh, I guess it did for me. Hang on. No, this is what I want. Sorry. My channel. Nope, that's not it. Hang on. I've got it on my computer here. No, I don't. Shoot. Hold on. I'll find it. Don't worry. Here we go. Add account. That's me. There we go. Oh, stop. I don't want to keep my... No, skip. Thank you. Making it hard for me, Google, I tell you. Of course, Google's going to parse this, and then they're going to smash my YouTube account. Okay, where'd it go? Now, there we go. YouTube. Okay, YouTube. Oh. Right. My channel. There. That's still not it. Hold on. There it is. I did the new account, but I just didn't switch to it. And let's see. So now I can do my channel. It should come up with my right channel. And there it is. Not the stack. This. Okay. Does anybody know Professor Shapiro? Yeah, he's in the School of Education and also computer science. He's got this new puppy, and he actually works on. He's a resident advisor, and he brings his puppy in every so often. And he named the puppy, literally named it Jumbo Jr. And hang on. Why is this not? Hang on. You got to hear the sound, because he does the cutest little bark I've ever heard in any dog ever. Hold on. There it is. Okay. Ready? I'm going to read. Okay. Listen for the bark. Isn't he the cutest thing you've ever seen? He's like this big. And he's only going to get like this big. And his little tail goes, whoa. All right, yeah, so that's Jumbo Jr. I will see you guys in lab or on Wednesday.